This afternoon, on our theme day of 3D imaging, we are honored that Dr. Hong Hua from the University of Arizona College of Optical Sciences accepted our invitation to be plenary speaker. With over 25 years of experience, Dr. Hua is widely recognized through academia and industry as an expert in wearable display technologies and optical imaging and engineering in general. Let's welcome Dr. Hua.
Good afternoon. Thank you so much for the very kind introduction, and it's truly a great honor for me to speak here today. Let me open this conversation by saying that we humans have always been very obsessed of creating visual illusions and experiences that are different from our reality. And we often do this by rendering artificial visual cues that trick our visual system to believe we are in some type of different reality. And for example, back to 1838, Sir Charles Weston proposed this concept of stereoscopes, which allow a viewer to be able to see a 3D image through a pair of stereoscopic images. This concept of the stereoscope actually evolved into today we call virtual reality. And of course, this view experience has evolved greatly from presenting a static stereoscopic photograph to fully immersive, interactive experiences in exotic digital worlds. And today, with the much more powerful computing capability, the experiences we are able to create becoming very engaging, and VR experience started to reach to the massive consumer market. Parallel to the VR creation, we are also interested in creating a different visual experience where we want to superpose digital objects into the physical reality and trying to create something that interactive experiences between the atoms and the bits, between the physical and the digital worlds. And this can be dated back to the days in 1968 when even Sutherland demonstrated a sort of demicles which essentially is an optical see-through head-mount display, but through which you can see computer-rendered wireframe objects superposed into the physical reality. And of course, this experience has evolved into what we call today augmented reality. And the experience, of course, has greatly evolved from wireframe objects to fully graphically rendered characters, objects, from Magic Book to Pokemon Go. Probably many of you or many of your kids have played that game in the last couple of years. So as said, we crave for visual experiences, and we never stop. And so the idea of back to 1997, a professor from Columbia University demonstrated this mobile AR system, essentially packaged the GPS tracker display computer system in a big backpack so the student can bring that on campus to be able to experience a larger scale, more engaging experience between the digital and the physical worlds. And so this experience evolved today into what we call the mixed reality or the spatial computing experience. And of course, today we hope to reduce the whole package of technology the student carry, along with many new components, depth sensors, wireless technology, and more powerful computing, and many other sensors into a small package. Create a different platform, or the spatial computing platform. And through this platform, we want to create visual experiences where we can live in harmony with our family, friends, with the dogs, and with seahorses, sea turtles, and dinosaurs in harmony in your living room. And creating this type of compelling spatial computing experiences, however, is very challenging, and it relies upon many key enabling technologies. In last year's keynote speech, Dr. Ron Azuma actually had a fantastic summary of the key challenges, obstacles that for creating consumer-level AR applications and systems. But among all the different challenges, a lightweight, non-intrusive, and comfortable display technology probably is one of the most critical and perhaps most challenging enablers in that suite of technology. In the last 20-some years, I have been working on some of the problems, and among those problems, and I personally believe addressing the vision discomfort problem associated with wearing this display technology probably is one of the most pressing obstacles. Because we are putting this per display, presumably in our daily life, and more interestingly, many of us probably have been aware of this myopia epidemic problem. And it has been documented that over 90% of teenagers and young adults in East Asia countries are nearsighted. 50% of young adults in Europe and the US were nearsighted. And experts predicting by 2050, 50% of our population are going to be nearsighted. This type of scene probably are not strange for many of us who have young kids. This seems to become the norm of their social life today. So glue their eyes on iPhones and iPads. Well, if we're saying that's too much screen time, wait until we have the kids have access to a VR headsets, have a spatial computing platform, being able to create an environment, interesting, engaging experience in your living room. It's going to be very difficult to take them away from the device. Well, before it becomes too late, we probably should spend some time to actually tackle the problem and trying to understand the vision discomfort problem and trying to address the problem before it becomes an even more epidemic problem. So that's the topic I'm choosing to focus on today, a quest for vision comfort. There are many different factors that could potentially contribute to vision discomfort when you wear a VR AR display. And the topic I'm going to spend most of the time today is going to be a topic that I would say I accidentally identified and then found very intriguing, and I worked in the last 15 years. So back to something around 2003 and time frame, I was working on a type of technology we call a head-mount projection display. Essentially, it's a head-mount projector projecting images onto a reflective screen. That's not the point of today. But however, we were using that device, the device is showing over here, and building all kinds of interesting UI interface devices to work with AR. And one of the devices that we were really liked about was a handheld device that mimic the function of magnifier in an AR environment. In order to make it work, the device is just something like this, coated with the reflective film. And we have been doing a number of studies, and one of the studies we were trying to investigate how this device could help user interface in AR. And we ran a study with 20-some subjects. So, and then over half of the people participating in the study complained that at some point in the study, they had a difficulty fusing the stereoscopic image, being able to distractively start to see a blurry image or two separate images. And we were puzzled at that time. What was the problem? Because we ran similar studies in other AR displays before. And after some investigation, we found the problem was the focusing problem, the focusing cue problem. Was because on this screen, those markers I showed on the screen were not supposedly be there, but they are markers produced by the vendors of this film as a protection and to their trademark. But however, it produces very strong focusing cue to the user and force the subject to tend to focus on the surface of the device, which we are rendering 3D images supposedly pop up from the device. And the image rendered through the display was displayed meters away. And so, but these markers force them to focus on the surface. And so this conflicting issue actually break that experience, made over half of the people were not able to do the study. And that taught us a lesson and become an interesting problem for me to study in the last 15 years. That's how it started. So now let's formally introduce what was the problem. So when we use our eyes to see a real-world environment, let's say you look at the beach ball and the cube. If our eyes interest in the beach ball, your left and right eye will turn to the beach ball, converge to that depth, and then the eye lens in your eye is going to accommodate and focus on the beach ball. And the object, the cube, as the light rays from that is going to form a blurry patch, and then therefore your retina image will look something like this, a sharp beach ball and a blurry cube. Vice versa, if you shift your focus to the cube, then you will see the opposite effect. So during that process, three things happened. Vergence. So your eye, left and right eye, will turn your visual axis to converge at a depth, and we usually measure that with the vergence angle, which is inversely proportional to the depth and also proportional to the interpupillary distance. Then they associate with that is accommodation. Your eye always, accommodation and vergence is coupled together hand to hand. When your eye verges to a depth, your eye also tend to accommodate at the same distance. And what happened, the third thing is the retinal blurring here. During that accommodation process, when the objects at the depth of the focus form a sharp image, but the object at a different focus is going to create a blur. That blur actually is the cue that drives your eye to accommodate. But what happens when you plot that relationship, Vergence-Accommodation, in a natural view condition, that tends to be a diagonal straight line. We all know that. To most of the conventional HMDs, however, this doesn't happen. So you have a macro display. Typically, the eyepiece magnifies the macro display, create a virtual display. That virtual display is fixed at a fixed distance away from the viewer. It doesn't have the ability to change focus. So consequentially, when you use this type of display, render 3D, and you use your eye is cued by the virtual display distance to focus to accommodate at the depth of the screen. But in the meantime, the binocular disparity you rendered for the objects, trying to drive your eye to converge at the depth of interest. So that to depth typically is at different distance, right? And so now if your eye focus, if you're trying to go back to the plot and remember the example and the experiment we were trying to run, in that system, the virtual display was set about 3 meters away. And so according to the clear vision fusion area, only objects within that green area, the user would be comfortably fuse them as a clear stereoscopic image, while object rendered at other depth will not be able to fuse comfortably. But the thing made it worse was the markers on the screen, which create a completely different focusing cue that forces your eye to focus at another distance. And so that essentially was from that experiment tells us that focusing cue in stereoscopic system is very important. And actually, many psychophysical studies have demonstrated previously with the stereoscopic displays and reported artifacts like a distorted depth of perception, eye fatigue, and so on. But what is very important in AR applications, the focusing cue in your AR environment is ubiquitous. You see a focusing cue everywhere in your physical world. And any mismatch of focusing cue with the digital world is going to create a conflict, and the conflict is going to break the experience, just like the experiment we were doing. So with that being said, in AR applications, addressing the focusing cue mismatch problem is much more critical than just having a virtual world alone. So since that time, 15 years ago, we found this problem and started working on this problem. And of course, many other groups have also been working on this problem. There are many different approaches have been developed. And so this article I wrote a year ago was basically the overview about what are the existing technologies that people have attempted to address this problem. So one of the methods is to, since the conflicts of accommodation and convergence, so one simple way to address this problem is reduce the needs for eye to accommodate, right? So if you can extend the depth field of the display, your eye do not have to accommodate in order to see it. So you work in a kind of relaxed state, maybe. So, for example, one way to do that is to reduce the rebundle size that enters your eye pupil. And so then basically essentially reduce the D diameter from that each pixel. So one simple way to do so is use a pinhole optics. You apply pinhole optics at your entry point of your pupil, only allow a very small rebundle coming from a single pixel. The Maximilian view display or the pinline display basically uses this principle. Versus you can also engineer your system so that your point spread function, the perceived retinal image point spread function, doesn't change, doesn't matter where you focus on. So this, for example, the group at Stanford University, they incorporated a focusing tunable lens, and they oscillating the power of the tunable lens between a far state and near state so that the eye sees a constant blur. So therefore, the PSF doesn't change. So this, either you use pinhole optics or use an engineering PSF approach, you do not create focus cue. You just reduce the need for focusing. A real mitigation to this is you should train engineering technology that actually create focusing cue. The simplest way to adopt in the conventional HMD system might be just a vari-focal solution, where you add some mechanism allow you to change the apparent distance of the virtual display. So this can be done by you add a motor or actuator on the macro display so that you can adjust mechanically the position, the actual position of your macro display from the lens, therefore change the apparent distance of the virtual display. Or you can add a motor to drive your lens along the axial distance direction so that you can change the virtual display. A more convenient way to do that is to, when you design your eyepiece, integrate a tunable lens, which you can control its optical power by applying electrical signal. And this was the approach we attempted to do about 10, 15 years ago. And this demonstrates one of the examples. We use a liquid lens in the design of the eyepiece. By adjusting the power of the liquid lens, that changed the apparent distance of the virtual display. This video actually, is it playing? I hope so. No? Played fine. Well, anyway. So the prototype was showing on the picture on the right side. I'm starting to get it. So what you saw from here was we integrated a left eye. Why is it doing that? The left eye and right eye tracking system in order to know where the eye has been converged. So therefore, we drive the liquid lens in this triangular form so that the virtual display will be moving along the visual axis from far close, but at a relatively slow speed. It depends on where your eye is looking at. And utilizing the binocular eye tracking, we were able to determine the point of convergence, basically where your eye has been converged. We adjust the focusing of the display to match with the convergence. So that in this demonstration, we were able to render the bunny when the eye is converged at the near, or we can render the bunny converged at the far. And then we rendered artificial blurry. Using that prototype, we also did experiments to validate whether focusing, because at that time, I was still not strongly believe whether this is going to solve the problem. So we did experiments to see whether this actually truly helped to improve some of the artifacts. So one of the study we did was to measure perceived distance, because that's one of the standard way people have been to quantify some of the artifacts. So we end up having a result very nicely. If you plot the perceived distance versus the accommodation Q of the distance you rendered, and you turn out to be a very nice diagonal line with a slope of 1. And we also measured the eye accommodative response with the autorefractometer. And it turns out the eye actually can, as you change the apparent distance, your eye accommodate correctly, driven by the distance that is provided by the display. So that was very encouraging. The only problem with the Vari-focal is a very easy fix, but however, it doesn't render an extended 3D volume with the correct focusing cues. So we started looking into other solutions. One of the solutions we look into is known as the multifocal plane approach. So in this way, instead of just render one focal planes for the system, you change the position based on where the eye is looking at. So now we render a stack of focal planes. And by slicing the 3D volume into slices, each of the slices provide a projection of a very thin volume. And then collectively, this stack is going to render the whole volume, and your eye sees the integration of that. So if your eye end up to be focusing at a near point of the scene, then the rays from that focal plane is going to come into focus, and the rays from other focal planes will naturally be blurred. And so in this case, you don't have to use eye tracker to know that this is also naturally correct focusing. So implementing this technology, typically there are two different ways. One, you can do this spatial multiplexing approach. You can stack multiple physical display sources together in space. So for instance, a group at Berkeley demonstrated a 3 focal plane system by subdividing a display using a stack of 3 beam splitters to create 3 displays at 3 different distances. Or you can use a time multiplexing, creating a stack of focal planes by rendering them one at a time, but at high speed, so that your eye sees them as if they were rendered together. So we modified the early prototype we demonstrated with the Vari-focal by driving the liquid lens at a different way. So you drive them at a high speed, but at 2 distinct focal distance in the stepwise way. And so by doing so, we were able to create a 2 focal plane system, render objects at 2 distinct focal depths simultaneously. And so it doesn't matter, depends on where your camera or your eye is looking at, you always get correct focusing. But the challenge was, how many focal planes do we need? And with the technology, how many can we afford? And can we reduce the focal plane to something that it can give you good quality, but also is affordable with the technology? So we end up looking into a different phenomenon where we call it depth fusion technology. We're using the fact that if you have 2 discretely separate focal planes, if you can modulate the light contrast between these 2 focal planes, you can actually render a perceived image or a fused image that actually appeared to be in between. So the system that we demonstrated was we were able to create a 6 focal plane depth fused system and render a volume from 30 centimeter to optical infinity by using 6 focal planes. And the prototype that you saw here, basically, the video on the top shows you how the image got rendered. They separated into slices, but then they were fused using this fusion function, nonlinear modulation function, to create a continuous blending of the 6 focal planes. And of course, the challenge of that technology, this probably so far is the approach that gives you the highest image quality and the correct focusing cues. But it requires you have high-speed macro displays. For instance, in that one, we use a DRP, but we were using the high frame rate of the DRP, being able to render 6 focal planes. So each frame needs to be, each field focal plane needs to be rendered at 360 hertz. And we need a high-speed adaptive optics, and we need the graphics to be able to render in high speed if we want to do that in real time. Another approach that we have been investigating in the last few years was the 4D live field display. So the multifocal attempt to slice the volume along the Z direction. You can think of the light field, 4D light field display trying to render the light rays, sample them in the angular direction. So for instance, in order to render this cube, if I can render the different ray directions appearing coming from the point on the object, so then if my eye is focusing at a point, some sub-bundle of the rays will come into focus. The rays from different object point will not be in focus. So in terms of implementation into the HMD platform, there are essentially 2 different ways. Integral imaging in the sense that you stack a macro display with either a lens-lit array or pinhole array or some type of array optics. And so then you can either directly place that in front of your eye as demonstrated by a prototype by NVIDIA, or you can insert an eyepiece of some sort to be able to magnify, use the in a way that I think of the macro display and the macro lens lit array, create a 3D small miniature light source, and an eyepiece magnifies it, give you a much bigger depth field. And also this can be done by a stack of spatial light modulators, like the group at Stanford demonstrated using trying to computationally generating the light field rendering and on the different spatial light modulation layers and being able to render the individual ray directions. So before I start to tell you about the engineering reality of this type of technology, and I want to show you a proof that light field display, if you build in high quality, it truly works. So the one that I'm showing here is a prototype built by Intel Labs. They call the Intel Lab light field display print. And the print, you can see the video shows the cameras was moving around and you were able to see the correct focusing cues. But the key to this is the print was made from a lithographic plate with a pixel size of 1 micron. In other words, the density is 25,000 ppi. And the macro lens lit array has a diameter 0.25 millimeter. That gives you equivalent, you have about 49,000 pixels under each of the lens lit, right? And the apparent resolution after the lens lit magnification was about 100 ppi. If you view that at 500 millimeter away, which gives you about 1.7 arc minutes. And the view density captured by the camera aperture was about a 10 by 10 views, means 100 views coming from one object. Well, is it practically possible with today's display technology? Let's say we use today's best macro display. It's about 6,000 ppi. Pixel density. And if we try to keep the macro lens lit array parameter the same, not mentioning whether it's feasible yet, and the spatial resolution we can create with today's macro display is about 24 ppi, equivalently about 7.2 arc minutes if you view it at 500 millimeter away. Not great, but okay. But if you use a bigger pixel, obviously it's going to be much worse. So, and a few years ago, of course, at that time, I don't know the Intel live field print yet. But however, when we started developing that technology 5 years ago, I want to ask I know it's a difficult problem, but I want to ask myself and my students, can we actually practically build live field head-mount displays that have reasonable performance? What type of quality, in other words, image contrast, resolution, depth of field, can we get from this type of live field HMD? And how does the image quality change with targeted depth? Can we actually create an extensive depth volume like what we did in the multifocal plane display from very close to very far? And can we get a scene, render the live field display, very deep live field display with consistent quality? And how does that quality change with the different sampling strategy? Then because my goal was to address the vision comfort problem, so naturally I want to ask, if I build a practical live field display, can it actually produce correct focusing cue to stimulate your eye to accommodate to the distance you want? And how many different redirections can you minimally need in order to actually reconstruct the live field that can simulate proper eye accommodation? And then what's the balance between the two? So of course, I don't want to build, and also it's not I don't want to, I don't have the budget to build tens and thousands of different prototypes to test it out. So we end up build a model to simulate them. So the way that I think of a live field, each of the ray is defined by 2 points on 2 planes. The ST plane usually consider the position sample of the ray, and the UV plane consider the direction sample of the ray. So since in the next session, I'm going to talk about how to model the retinal image formation for live field display, essentially this technology, then I'm going to just generally talk about the things that are important for you to be able to understand some of the simulation I'm going to show you on the next few slides. For this one, I'm not going to talk about the detail. So for instance, generally in that 4D representation, you think of one sampling was done on the rendering plane, which essentially are the pixels that render the elemental views. For example, in order to render a 3D point P, I happen to have 4 different views. And then the modulation plane essentially is the array optics, macro lens array, pixel array, doesn't matter. So the central depth plane is the optical conjugates of the render plane, is what your eye directly sees. So so the 4 pixels coming into focus on the central depth plane, and then the rays is going to continue propagate and intersect at the point of P, which is your depth of reconstruction. And then the cone of light projected onto your eye pupil. Your eye pupil sees multiple different views. And if your eye accommodated at the depth of reconstruction, these 4 separate points, spatially separate points, come into focus becoming 1 point. Or if your eye accommodated at different distance, these 4 separate points becoming separate, creating that blur effects we are hoping for. So as you can see, the accommodation in this case is very important. So essentially, in terms of sampling, there are 2 different aspects of the sampling, the redirectional sampling and the repositional sampling. The directional sampling are essentially defines, we use the view density to define the key aspect of it. That essentially basically means how many views your eye can see at a given time. And then the sampling also depends on the field factors of your view. For example, if the 2 views within your eye pupil were next to each other, or they were, even though the separation were the same, but they were not exactly next to each other, or the shape doesn't naturally be circular aperture, could it be slate apertures, and so on. So the next few simulations I'm going to show you, trying to give you some insights about how this directional sampling affects the image quality. So in this simulation, what I'm trying to show you was typically in the live field reconstruction, when your reconstruction is at the central depth plane, you tend to get the highest image quality. So this one will be showing you, the video here is showing you, trying to show you the effects of, by increasing the number of views, what is the perceived retinal image you will see through the live field display. And the left shows the point spread function, the right side is a simulation of the image. You can see, if you continue to see the top shows the number of views. For example, this is a 2x2 view, and I hope the video, and 3x3 view, and did it go? I don't know how this, and then 5 views, 5 by 5 views. As you can see, as the number of views increasing, the point spread function becoming bigger and bigger. That's natural. And that means your image quality is going to reduce. This is primarily due to diffraction effects because you are subdividing your eye aperture into small areas. And then another effect typically happens in this type of display. As your reconstruction depth is away from your CDP, the central depth plane, you are expecting to see even stronger degradation of image quality. And so the video showing here were a comparison of 2x2 view, you started with the CDP at 1 meter away, but then I shifted the reconstruction by 1 diopter increments away from the CDP. You see that especially for the 2x2 view, as you shift away, the point spread function becomes spread out. And of course, the 4x4 view has a larger depth of field and spread much slower. And the key for the live field display is trying to render focusing cube and the blurring cube. And so this is trying to show you the effect. If you fix your CDP, you render object, and then you start changing your eye accommodation, your eye accommodate from a different distance, how does the blur look like? And so the top one shows a 2x2 view, and the bottom shows a 4x4 view. You can see that for the 2x2 view, as you start to shift away, the blurry cube no longer look natural. The 4 points become 4 separate points that create artifacts in your image. Another aspect that we were interested in were the positional resampling. So positional resampling in one aspect is equivalent to the pixelation effects in a 2D display. But for live field display, it goes beyond that. The repositional sampling is going to cause missampling of your live field. It actually not only causes degradation of the image quality, but also is going to cause a incorrect depth of focusing. So this simulation was trying to show you the effects of the pixel sampling and for different number of views, for 2x2, 3x3, or 4x4. And if your display have infinite high resolution versus if you have 3 arc minutes or 12 arc minutes type of effects. And I'm not going to get into that detail. We have an upcoming paper, probably will be published in a week or two. And you will be able to see more details on that. But one point I want to point to was the accommodation response in relation to the resolution sampling. If you have infinite high resolution display, and so what the graph was trying to show you was the amount of accommodation error is typically increasing as your contents is rendered away from the central depth plane. But however, if it's even a high resolution display, that change is a smaller scale and continuous. But if it's a pixelated, and your accommodation error tends to change in a much larger scale and fluctuate because the missampling of the live fields. So based on many of the simulations, we started to build a prototype to see, because one of the conclusions we came is that we want to have a balance between the number of views and the quality. We end up build a system that have 2x2 views, and the 2x2 view within 3 millimeter pupil. And trying to get a resolution as high as possible, the system maintains a 3 arc minutes resolution. And the optical layout is showing over here. So it has the macro integral imaging unit. And it had a unit we integrated a tunable lens that allow us to adjust the position of the vari-focal plane. I'll show you some interesting use of that. And then it has the freeform eyepiece. So the prototype looked like something like this. It's very compact, and the prototype, this one on the bench, and this is the model on a real size head. And I want to show you some results of that. So in these videos, what are you seeing? So the top 3 videos were showing when the CDP was fixed at a different distance. For example, a 30 centimeter and 1 meter, and then 2 meters away. And so then, every time I touch it, it will move things around. So for instance, if you look at this video, if the CDP and 3 diopters, the the camera was changing focus back and forth, but you get the sharpest image at 3 diopters, and then when it goes back to 0.5 diopter, image converged, but blurry. And the video showing here, we call it a multiplexing. This is taking the idea of multifocal plane, but here is applied to the light field. It's a switching between the 2 focal planes. So now you can actually naturally get, when the camera was focusing at 0.5 diopter, 2 meters away, this image end up being in sharp focus, or if you switch to 3.5 diopter, you get sharp focus. I want to point out those Snelling letters. The top one was very tiny, 3 arc minutes, very small strokes of lines. And that was the limit of that display. So basically, we were able to, you can almost be able to see the 3 arc minutes in those captured picture. With the naked eye, actually, you can see better. The display was able to maintain that good resolution across that 3.5 diopter range. And let's compare to the Intel light field print. So this is when the light field print was focusing at the closer end of the object. And this is when the display was focusing at the closer end of the object. And you can see this was the Intel light field print had about 3 arc minutes angular resolution at a 300 millimeter view distance, and ours was 3 arc minutes at that distance. So it's a similar quality. We were able to get the good quality there. And then if you look at the blurry at the far end of the object, the blurry was acceptable. But however, if you compare to the focusing, if the camera was focusing at the far end, and then the blurry, this artifact is noticeably stronger than in the light field prints, they have natural blurring because they have about 10 by 10 views. We only have 2 by 2 views. The view density was much lower, but we get a constant quality. So now, the current prototype we built had a 30 degrees of field of view for the light field display, had a 2 by 2 views over 3.5 millimeter eye pupil, and together within the eye box had about 3 by 3 views, and had an angular resolution 3 arc minutes over the depth range of 3.5 diopters, eye box 6 millimeters. The question I want to ask, what does it take to scale that technology up? If we want to get 100 degrees of field of view, if we want to get 3 by 3 view, or even more than that, and if we want to get 1 arc minute spatial resolution, if we want to increase the eye box, those becomes very different equations to play with. Let's start with, so the current technology was implemented with a micro display with a pixel density of about 3,000 ppi, 8 micron pixel, and HD resolution with the 2 by 2 views. If we simply want to, if we keep the assumption that the panel size are going to maintain the same, view density keep the same 2 by 2 within the eye pupil, in order to get 1 arc minutes spatial resolution for the same architecture, we would need to have a macro display with about 9,500 ppi. I put a yellow color because it might be reachable in the next couple of years. If we want to scale that field of view up and the resolution up, 1 arc minutes, 90 degrees of field of view, we end up need to have a display had at 28,000 ppi, which is becoming to reach the point of the 1 micron pixel size in the lithography plate, which I do not have the confidence that we are going to reach to that point anytime soon, right? The other thing is the form factor. And I'm sure the technology that we have today, only myself and my students want to wear that. And none of you probably do not want to wear that, especially as a social technology. And unfortunately, optics do not have the Moore's law, and we do not have the ability to scale that down very quickly. And so that's one thing that becomes difficult. The other thing that I want to mention, I put this as a challenge / opportunity for vision correction. This chart showed you the percentage of people who need vision correction. And by the end of the day, the people with the normal vision was only about 25%. So of course, right now, the live field display we demonstrate was optimized for normal vision. And so can we do something about it? So actually, I put it as an opportunity because the way the live field being rendered is because you perceive the image depends on where your eye is looking at. If you slightly manipulate those pixels in each of the direction, you could change the way where your eye accommodate. In other words, I might have an opportunity to optimize the rendering for different users who needs different vision correction. This concept actually had been demonstrated years ago with a different technology, but was using pinhole array onto a cell phone device to demonstrate the ability to do the vision correction for this architecture. But essentially, we could use some similar optimization algorithm applied to the live field display for the rendering purpose. But of course, that needs to be worked out. Another facet of a challenge, and the focusing cue is not the only one that causes vision comfort. And so this problem is a different one that today most of the AR display, this is actually a typical AR view captured through an optical see-through device. You see a ghost-like image floating in front of the real-world scene. The cues between the physical and the digital is confusing. And that's believed to be one of the other cues that cause you some level of vision discomfort. But however, implementing something to fix that problem is not easy. And we have done some per pixel occlusion capable HMD. And so for instance, back to 2003, a group in Japan demonstrated a prototype of occlusion capable HMD that allows you to render the physical light and the virtual light correctly, but of course that's not what we want. Recently, we have demonstrated a prototype being able to make that much more compact. The effect was good. This is before you have occlusion. The bunny inserted in the environment was ghost-like. Now you were able to, because I'm able to control the light interaction in the pixel level, I'm able to do that mutual occlusion correctly, but the optics is not easy. And putting that together into the live field architecture is even more difficult. So now let me back to this point, 1965, 1968, even Sutherland demonstrated the AR display. And now we have a number of commercial products out there. And by 2020 and beyond, we probably are going to have many of them. But before we put that to the hands of the kids, and let's try to tackle this vision comfort problem from as many aspects as we possibly can. Let's evolve our vision experience, evolve the computing experience, but don't let the technology evolve our own eyes, and so that we have to adapt it to become very myopic. That's the end of my talk, and this is the group of students I currently have, and also many other alumni. Thank you.